This video will cover 4 items: a full 3D tool creation, an NC-Simul tool creation with a 3D holder, building up a master tool library, and associating tool libraries to specific machines. Even though NC-Simul can automatically transfer tools from all major CAM systems, this can be useful for unique mill models, specific turning tools for a more robust representation, or manual machining processes. Open an existing project or start one from scratch by hitting New Simulation Project from the File menu. Use an existing tool list or create a tool list from scratch. Give the library a name and choose the default values for the tool radius compensation and tool length compensation. 0 is running centerline, where only the wear value is put in at the machine, whereas radius uses the full value input. Length is either full gauge length or to the center of the ball radius. These can also be changed on a tool-by-tool basis later. The first example will be building a tool entirely from a 3D model. Expand the window with the Options button and begin in the 3D Objects tab. Each click of the green plus sign will allow for the import of models to an individual layer. Mind the CAD unit for scaling purposes, choosing inch for STL files and millimeters for step files. Note that a step file will have built-in layers for selection within a tool assembly, whereas an STL file needs the layers saved individually ahead of time. Here, the first 5 solids are part of the holder, so select those and hit Apply. Then, add a second layer, re-importing the same files again, however, this time only defining solid number 6, representative of the non-cutting portion of the tool. Repeat the process one last time, importing the same CAD file and defining solid number 7 into its own layer, which wraps up with the cutting portion of the tool. Since they are all on separate layers, they can be given separate properties going forward. The Position tab allows for the translation or rotation of the assembly attachment point, defined to snap to the spindle on the machine. Best practice is to put this at the gauge line before exporting the CAD file, but it can be modified here as well. Additionally, if the tool stick-out lengths vary between setups, it is possible to adjust the position of the tool relative to the holder. If the below box is checked, all assembled components will shift together. Frames defines the center point of rotation for the tool, mainly relevant when building right-angled heads, otherwise it will automatically take the location and direction of the Position tab. In Associations, officially define the properties of each previously created layer, the first one as holder, coloring it dark green, the second as non-cutting, displayed in light green, and the last one as cutting, represented in orange. The tool type of fixed or rotating is important when loading up mill-turn machines, and the subtype simply allows for the output of that information to NC-Simul's automatic documentation creator, NC-Docs. Parameters gives the ability to define the tool number and tool station, which is most important for turrets. The reference field is simply the tool name, a 10mm end mill in this case. Set the machining phase as roughing, semi-finishing, or finishing, depending on the tolerance setting desired during material removal. Each tool will highlight machine surfaces in a unique color, also customizable from here. Any additional data from the tool manufacturer that is input, such as max feed rate, material removal rate, or max width of cut, will be cross-referenced during simulation, and NC-Simul will throw an alarm if any conditions are violated. If the tool requires active coolant while running, or allows for through coolant, tick those relevant boxes, allowing NC-Simul to check this from the G-code as well. Values input in the Tuning tab give information for the Compensation tab to grab automatically. Again, it is best to retrieve the values from the CAD file for the gauge length and the compensation radius, if used. However, it's possible to visually walk in the gauge line to the bottom of the tool as well. Right-click on the arrows to change the incremental value of the translation and line it up with the model. Now, in the Compensations tab, the radius and length values are automatically calculated if chosen from the dropdowns, but zero and manually editing a value are still available too. The remaining tabs are dedicated to the toolpath optimization module OptiPower, allowing NC-Simul to calculate and regulate cutting forces. The second example will come in useful when having a set of standard holder models, but no associated or assembled tool models. In this case, construct a hybrid NC-Simul defined tool with an imported 3D holder. This time, in the first tab called Tool, choose a template like Standard for flat end mills, radiused end mills, and ball mills. Input a diameter value for the yellow cutting portion and an equal or relieved value for the purple shank section. Define the overall and cutting length, starting with the smaller of the two numbers. This can match the stick-out length from the holder or can match the physical size of the tool as shown later. Now, in the Holder tab, instead of a predefined cylindrical or conical model, choose 3D CAD file. Just as before, mine the units based on file type and import the step file in millimeters. This can be solely a holder file or the appropriate layers from a tool assembly. The Accessory and Parameters tabs remain unchanged from the first example, but this time the Tuning tab drives the relationship between the NC-Simul tool file and the imported holder file. Set the desired length under spindle, the overall gauge length, or length under holder, the gauge length minus holder size. Changing one of the numbers will automatically adjust them both simultaneously. Use this to test how much tool there is to hold onto or to match values as input at the real machine. As before, the Compensation tab will automatically find the length value or can be manually edited. Select Save to lock in all modifications and keep the tool library open. The created tool can be exclusive to this library, a specific machine, or can be repurposed and added to a master tool library location. To duplicate these two newly created tools, highlight them in the tool list and select the copy icon. Hit OK to close this tool library. From the drop-down, choose Use Tool List to access any previously created libraries and select the Developing Master Library. After opening, hit the Paste icon and all the created tool models and definitions will be added to the library. It's as simple as that. It is also possible to tell NC-Simul to always load a specific library along with a specific machine. From Add Resources or as part of an active project, load a digital twin machine. Right-click the machine name in the job tree and edit the machine. From the Associations panel, highlight the Tool Library File section and search for the completed .tlib file. Now when the machine is selected, the tool library will automatically be loaded under the tool magazine. Within a project, it's also possible to stack libraries or add a one-time custom tool, then increase or decrease the priority that NC-Simul selects one for use. Open the magazine and consult the project to see a full list of all available tools in the two active tool libraries. When G-code is added to the project, it will automatically pull tools for use based on the defined priority settings and tool number or reference calls. From here, you can also load or swap out any tool manually if there are tool variations with the same number. And that's everything that needs to be known about creating 3D tools from an assembly, combining NC-Simul templates and holder models, gathering and assembling a finalized master library, and associating that library to always run on a machine that contains a standard set of tooling.